Hi, thanks for joining me. Today I'm going to be doing a number theory problem which is based off of Fermat's last theorem. So if you've not heard of Fermat's last theorem before, it considers this equation here, x to the n plus y to the n equals z to the n, where x, y, z and n are positive integers with n at least 3. And the theorem says there are no solutions to this guy here. In today's video we're going to kind of be flipping the equation, so swapping the x and the n, swapping the y and the n, and swapping the z to the n. So considering this equation here, n to the x plus n to the y equals n to the z, with x, y, z and n all positive integers with n at least 3. And I claim that there are no solutions to this guy as well, and I'm going to prove that in today's video. Let's get stuck in. Okay, so unlike Fermat's last theorem, we can actually solve this problem in just a few lines. The first thing we notice about this equation here is that x and y are symmetric in the sense that I can swap them and that doesn't change the equation, because if I swapped x and y here, I still have on the left hand side n to the x plus n to the y, just rearranged. Okay, so I can assume without loss of generality that x is less than or equal to y. Like so. Cool? Then what I can do is just divide this top equation here by n to the power of x. So if I do this whole equation here, divide it by n to the power of x, I get 1 plus n to the y minus x equals n to the z minus x, like so. And hopefully you can see that this is kind of problematic. Let's see why. Well, if we have that y is strictly bigger than x, so we're assuming that y is bigger than or equal to x, but if now we suppose, just for now, that y is strictly bigger than x, well then if you look at both sides mod n, on the left hand side we have 1 plus 0, because this will be a positive power of n, and this right hand side is certainly a positive power of n, because z is certainly bigger than x from this line here. So the right hand side then would be 0 mod n, this is 0 mod n, and this is 1. So we have 1 equals congruent to 0 mod n, but this is certainly not possible because n is at least 3. The only way this could be possible is if n was 1. Okay, so this is not true, so y cannot be bigger than x, so we must have that y equals x. And of course if we just plug that into this line here, y equals x, that obviously tells us that y minus x is 0. So we have 1 plus n to the 0, which is 1 plus 1, which is 2, and that equals n to the z minus x. So n to some positive power, positive integer power, and n is at least 3. So this is clearly not possible because 2 is a prime number, it's less than 3. The only way we could have 2 equals something to a power is if this right hand side was 2 to the 1 or something like that. But that would require n to be 2, and n can't be 2 because n is at least 3. So we solved the problem. There are no solutions to this guy with x, y, z and then positive integers with n at least 3. And in fact the only way you can solve this, if you perhaps get rid of this condition, is if you make n equal to 2. Anyway, I hope you've enjoyed this quick number theory video. Thanks for watching. I'll catch you in the next one. Have a great day.